Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
I'd like to introduce Abhinandan Das, PhD corner, what a graduate, what a PhD in corner. It's Johannes' student. I did his undergrad in IIT Bombay. It was actually Sudarshan was his undergrad advisor. And his thesis is on approximation techniques over streaming data. He's going to talk about application of some of those techniques in the context of streaming spatial data.
So he actually survived all the bad advice he got as an undergrad.
Huh? basically, he's going to be judging this stuff as well.
So thanks, Raghav. So as I said, I'm going to be talking about online approximation techniques for spatial data. So with the advent of geographical information systems which manage spatial objects such as map data, spatial databases are becoming increasingly common. And should I switch on the mic? Or?
No, it's on.
Spatial databases are becoming increasingly common, and users of spatial databases can pose fairly expressive queries, such as find all objects which are within a certain distance of each other, or find all pairs of objects that overlap, and so on. So here's an example to illustrate the kind of spatial queries that users are typically interested in. Consider a dataset containing information about land cover in a country or a state. In this case, the state is Wyoming. And the land cover objects are depicted in a color-coded fashion, with each color representing a particular type of vegetation. And consider another dataset containing information about the different regions in the state. So in this case, it's shown in the form of a grid, but these regions need not always be rectangular in shape. So a typical query that you might be interested in is the following overlap join query. Find the types of vegetation found in every region in the state. So in order to process this query, what you need to do is, conceptually, for each region you need to find every vegetation object which overlaps with it and output a tuple for every such pair. So I've just zoomed into one of these regions to give you an idea of the nature of the objects which are involved. So each color here represents a particular type of vegetation. So as another example of spatial queries, consider the following example taken from the Cornell Lab of Ornithology. So on the left you have places in the US where the American crow was spotted in the year 2003. On the right you have places in the US where the American goldfinch was spotted in the year 2003. And a query that you might be interested in is find all locations and times where bird X, say the American crow, was spotted, and the bird Y, the American goldfinch, has been spotted at a nearby location, say within 50 miles, at a nearby point in time within a week. So here you're interested in finding all those pairs of points which are located close to each other. And there's also a temporal aspect, this week, which can be treated as another spatial dimension. So due to the spatial extent of objects, processing queries over spatial data is usually expensive. And often there's a very large amount of data involved. For example, Microsoft's TerraServer project indexes close to 400 million spatial objects. And these are, I think, one-year-old numbers. So just as in relational database systems, for spatial databases also, you're interested in having accurate selectivity estimates of different queries in order to choose between different execution plans. And the difference between a good plan and a bad plan can be several orders of magnitude in running time. And there are two main summary structures which have been proposed for summarizing spatial data. They are histogram and samples. But none of the proposed techniques in literature provide any sort of error guarantees on the quality of the estimates they produce, and they are also typically difficult to maintain incrementally in the presence of deletes. So why are these two things important? So clearly, if your dataset is very large, you don't want to be recomputing your summary structure every time your dataset changes. So incremental maintenance is important. Error guarantees are also important because these summary structures, for example, histogram samples, they're sometimes very accurate and sometimes they're off by orders of magnitude. And there is no way of knowing in which case you lie. So you can't really rely on the estimates provided by these summary structures. However, there's a more important practical reason why you want your summary structures to provide error guarantees. So this is a graph taken from an EDBT 2002 paper which proposed the till then best known techniques for spatial selectivity estimation. So it compares the performance of the proposed technique, Euler histograms, with two other histogram-based techniques in estimating the cardinality of the join of two spatial datasets, two real-life datasets. So on the y-axis you have the relative error, and on the x-axis you have the grid level. So what these histogram techniques do, they typically partition the data space into a grid, and the grid level indicates how fine the grid is. So higher the grid level, finer the grid, and more is the space occupied by the summary structure. And you notice a very interesting phenomenon. In several cases, as the space given to the summary structure is increased, the error is actually increasing. In this case, this anomalous behavior is occurring because the estimation procedures that they used assume that as the grid size becomes smaller and smaller, every pair of objects that overlap a given grid cell also overlap each other, which need not always be true. This kind of anomalous behavior will never be observed with a technique which provides some sort of error guarantees, because typically there will be a formula which inversely relates the space required with the error guarantee. And robustness is clearly an important property required in practice, because in practice a system designer may not know in advance which part of the space his data lies in. So he may not know, for example, what is the optimal grid level to use. And you would not like it to happen that you give your summary structure more space and it actually does worse. So our objective here is to design summary structures for estimating the cardinality of spatial queries. We would like a summary structure to handle a wide range of spatial queries, overlap joins, range queries, and epsilon joins. I'll be defining what these are shortly, but these are similar to the queries I talked about at the beginning. We would like a summary structure to provide guarantees on the quality of approximations, and ideally we'd like it to be constructible in one pass with the input and incrementally maintainable. Because if your datasets involved are large, you don't want to be recomputing your summary structure every time there are updates. And note that if you have this property of one pass incremental maintenance, this could also be used for processing streaming data. So the outline of this talk is going to be as follows. I'm going to begin by describing the kinds of spatial objects and queries that we are interested in. Next, I'll introduce sketching, which is a basic technique used for summarizing data streams. I'll then talk about how one can construct sketches for spatial data. I'll begin with the one-dimensional case and generalize to higher dimensions. And finally, I'll conclude with the discussion of experimental results and a brief overview of some of my other work in the area of data stream processing. So by the way, feel free to stop me anytime with questions. So what are the spatial objects that we're interested in? So we will assume that the objects we're dealing with are hyperrectangles. Now it is true in real life, spatial objects are not necessarily rectangular in shape. However, in spatial databases, they are often represented by the MBR, the minimum bounding rectangles, for two reasons. One is for compactness of representation, and second is for efficiency of query processing. It is very expensive to check whether two arbitrarily shaped objects overlap or not. So typically what is done is in the first pass you check whether their MBR, the minimum bounding rectangles, overlap or not. And if they do, only in the second pass you go and check whether the objects actually overlap. So
do your techniques really, if I change the MBRs to circles, let's say spheres, will your techniques be practical?
Yes, they will work. So I'll be talking about two techniques. One of them will work, which is the more important one. There's a very naive possible solution. The not naive one will not work, but the naive one will work. But that has some space and time problems. Yeah, but the techniques, yes, the other techniques that the main contributions, they're probably not going to be working for circular objects.
What if you split an object to get multiple MBRs, which together cover an object?
Okay, and
would that make a difference to your technique instead of having one MBR?
So it depends. So finally, the way I'll be abstracting the problem is I'll be interested in counting overlaps of MBRs. Now, if you have one object which is given multiple MBRs, you'll be counting that overlap multiple times. So if that's what you want, you're fine. But if that's what you don't want,
maybe we'll come to it later.
Okay.
Hear your techniques.
I guess the point is then you can have more final way to model it.
Mm-hmm. Yeah, I guess that's what you're suggesting, right? Yeah, definitely. Yeah.
Since we're already interrupted,
Okay.
you said earlier on that samples don't provide any probabilistic guarantees. Why is that?
So samples do provide guarantees, but for spatial data, there are no known techniques for, say, joint selectivity estimation, which provides guarantees, which uses samples. And there are two main problems. One is it has to overcome the natural problem of join samples and not a sample of the join. So
okay. So basically, it's the join that allows you not to.
Yeah, but that is just one part of the problem. The second part of the problem is the spatial objects have spatial extent, and it's not easy to know. So in the case of point data, you know that a point which has a high frequency, you want to sample its partner so that you get these joint tuples. Here you might not have rectangles which occur very often. There might be rectangles close to each other in some way, but there's a very large other object which overlaps with all of these objects, which is why you want to keep this large object in your space. And there's no known, so it's conceivable that samples could provide guarantees, but so far there has been some work using samples, but they don't provide any guarantees. we'll assume that our domain is a, so any more questions? Okay. So we'll assume that our domain is a d-dimensional space n raised to d, where n is some finite ordered set, say the set of all 32-bit integers or the set of all 64-bit floating point numbers. So what are the queries that we're interested in? So the main query that we're going to focus on this talk is estimating the cardinality of overlap joins. Basically, if you're given two sets of multi-sets of hyperrectangles R and S, you're interested in estimating how many pairs of hyperrectangles overlap each other. So for example, if R is the set of red hyperrectangles, say in two-dimensional space rectangles, and S is the set of blue rectangles, then in this case, the size of the overlap join is going to be 3 due to the 3 shaded regions. We are also interested in handling queries such as epsilon joins. This is similar to the ornithology dataset query that I talked about. So A and B are two sets of points in d-dimensional space. We're interested in finding all those points which lie in a certain distance of each other according to some metric. So for example, if A is a set of points, red points, and B is the set of blue points, and assume that the points which are connected by lines are within your required distance epsilon of each other, the cardinality that we're interested in estimating in this case is 6. Finally, we are also interested in answering range queries. So if R is a set of hyperrectangles and Q is a query hyperrectangle, so R is the set of rectangles and Q is this query rectangle, you want to find how many rectangles in your data set overlap this query rectangle. In this case, the answer happens to be 5. So far what I've talked about is the kind of spatial objects that we're interested in, that is hyperrectangles in d-dimensional space, and the kind of queries that we're interested in. In today's talk, we're going to focus on estimating the cardinality of overlap joins. Next, I'll talk about sketching, which is a technique for summarizing data streams. So loosely speaking, a sketch can be described as a summary structure which can be constructed over a data set in one pass. It is incrementally maintainable, and typically sketches rely on randomization to provide estimates. The most well-known form of sketches are the AMS sketches or the tug-of-war sketches. So they call AMS after their authors. Alon, Matias, and Szegedy proposed this in '96 in their seminal paper. Let me show you how these sketches work. So let's explain how these sketches work with the help of an example. So consider a relation R whose tuples are streaming in, and suppose you wish to compute the self-joint size of R on some attribute A. So for example, suppose the domain of the attribute contains only 3 values, A, B, C, and these are the frequencies in the stream R. You're interested in estimating the size of the self-joint, that is, if value I occurs fi times, summation over I fi squared, because if value I occurs fi times, when you take the self-joint, it will appear fi squared times the self-joint. So in this case, the size of the self-joint is 14. So what Alon, Matias, and Szegedy showed that any deterministic algorithm to even approximate the self-joint size requires space proportional to the size of the domain. So self-joint size is useful, for example, for trying to estimate the skew in a relation, or it can also be used to derive bounds on the joins of two relations. And since due to this, and if your domain size, say for example, is the set of all 32-bit integers, using space proportional to domain size is clearly not feasible. So you have a problem with deterministic algorithms trying to estimate the self-joint size.
But should it be more than the number of tuples then? It's saying.
Yeah, it's minimum of those two, right? Yeah. So the main idea behind AMS sketches is to use randomization to try and beat this bound. And what AMS sketches try to do is they try to summarize the information in a stream with a single number, just one number, one integer. And this is this number that we'll be calling an atomic sketch. So what is this number? So the way it works is as follows. You select a family of independent plus minus 1 random variables. So you have one variable psi I for every value I in the domain of the attribute. And these psi I values take on values in plus or minus 1, which are such that the probability that psi is 1 is equal to the probability that is minus 1, which is equal to half. So it takes on these two values with equal probability. And on expectation, so psi I is 0. And the atomic sketch, which is the single number which we'll be using to summarize the stream, is nothing but the dot product of the frequency vector with the vector of size. And this can be computed very easily over the stream as follows. So you begin by initializing your atomic sketch x to 0. And every time you see a value I on the stream, you add the corresponding psi I value to the counter x. So for example, when you see the value A, you add psi A. When you see the value B, you add psi B, and so on. So at the end of the stream, x will have this value. And clearly, at the end of the stream, the value that x has is given by this formula here. Since the value I, if it occurs fi times, you would have added psi I fi times to your counter x. So this is the atomic sketch that we'll be using to summarize the stream. And now the claim is that x squared approximates the size of the self-joint of R. Let's see why that is so. So we've computed this quantity or the dot product of Fi, the frequency vector with the psi vector, and what we want is the self-joint size of R.
Is this probabilistic counting? Is this what's going on?
Yeah, definitely. So probabilistic counting is applied to, the term is used for something else, but this is similar. Yeah. So if you take x squared, writing the term with I equal to j and I not equal to j, you get this first term here and the second term. And since psi I is either plus 1 or minus 1, psi I squared is always plus 1. So x squared is basically this quantity here. And the first term is already the quantity you want to approximate, and you have an extra second term. So taking expectations, the first term is a constant and pushing the expectations through the second term, you get expected value of psi I, psi j. Now, since the psi i's we assume were independent, the expected value of the product will equal to the product of expectations, and they each had 0 expectation. So on expectation, you have the right value. And the crucial point here is the psi I values need not be fully independent, but only pairwise independence is needed. So note that in order for the expectation to be correct, we only require that the expected value of a product of two variables is equal to the product of expectations. We need only pairwise independence, not full independence. And so because we need this limited amount of independence, it can be shown that these psi I values can be generated from small seeds on the fly. So you don't have to store this vector of psi I explicitly. And this is important because if you had to store this vector of psi I explicitly, you would need space proportional to the size of the domain, which is exactly the problem we were trying to solve. So here's an example to help make things clearer. So you have a stream R which is initially empty. Your atomic sketch consists of this counter x, which is initialized to 0, and this pseudo-random number generator, which uses the seed to generate the psi values. So when the first value arrives in the stream, you feed it to the pseudo-random number generator, which generates the value of psi a. In this case, it happens to be -1. You add it to x. So x is just a running counter. Do the same for the next value. So when the third value a appears, the psi I value generated is the same as that generated when the first a value appeared. So this is a deterministic function. The randomness is only coming in because of the seed. It's a pseudo-random number generator. So you do this for every value in the stream. And finally, when you ask to return an estimate, you return x squared as your estimate. In this case, you return the answer as 16, whereas the 16, whereas the true answer happens to be 14. So note that though we are correct in expectation, our estimates may have a high variance, and so we may not always get the right answer. So in order to get arbitrarily close to the right answer, we use a standard trick called boosting, which basically tries to, instead of returning the estimate of a single atomic sketch, it keeps several independent estimators and returns the average as the estimate. And the number of copies, IIDs, so independent identity distributed copies that you need to average over, clearly depends on epsilon and delta, but also depends on this. Okay, I didn't explain what epsilon and delta are. So typically you get these epsilon delta guarantees, which is that the probability that your relative error is greater than epsilon. So EZ is the quantity you're trying to estimate, and Z star is your estimator. So the probability that your relative error is greater than epsilon is less than delta. These are the sort of guarantees you can get by averaging so many copies of your estimator. And the number of copies you need to average depends on the variance of your estimator. So you would like your estimator to have low variance. So earlier you had the single atomic sketch with a seed. You now have W independent atomic sketches, and when you ask to return an estimate, you do some sort of averaging and medians to return your answer. And it's this collection of atomic sketches that we will be calling a sketch. And just like you needed pairwise independence for your answers to be correct on expectation, in order to get low variance, you can show that you would like to have 4-wise independent random variables. And even 4-wise independent random variables can be generated efficiently on the fly using small space, logarithmically in the domain size. So this is not a problem. So let us see now how one can construct sketches for spatial data. So I'll begin with the one-dimensional case. In the one-dimensional case, we're interested in estimating the cardinality of the overlap join of two multisets of intervals. So a pair of intervals in one dimension can have 6 possible spatial relationships. They could be disjoint, they could just be touching each other, and so on. There are 6 possible spatial relationships. And we say a pair of intervals overlaps if the length of the intersection is non-zero. So in cases 3 through 6, we say there's an overlap. Whereas in cases 1 and 2, we say there's no overlap. So in this case, there's no overlap because the length of the intersection is 0. So since we are interested in estimating the number of overlaps, we would like an estimation procedure to return a count of 0 for these 2 cases, no overlap, and 1 for these 4 cases. So this is the vector that we would want your estimation procedure to return for these 6 cases. Suppose instead of estimating overlaps, you had a procedure which could estimate how many times the endpoint of one interval lies in the other and vice versa. This is the vector you would get. So for example, in this case, you get a count of 2 because the right endpoint of R lies in S and the left endpoint of S lies in R. Similarly, you get a count of, say, 4 in this case because each endpoint lies in the other interval. You get a count of 3 in this case. So this is the vector that you get when you count endpoints. Dividing by 2, the vector that you get is shown in the last line. And note that already we are very close to the quantity we are trying to estimate, to the vector. So in cases 1, 3, and 4, you already have the exact answer which you are trying to estimate. And only in cases 2, 5, and 6, you return the wrong answer. And note that cases 2, 5, and 6 are exactly the cases where the two joining intervals have common endpoints. So let us assume for now that the two datasets which join do not have, the intervals in them do not have common endpoints. Later I'll show how you can remove this assumption. But for now, let's assume that the two joining datasets do not have common endpoints. In that case, by counting how many endpoints of one interval lie in the other, you can accurately estimate the number of overlaps. So based on what I said in the previous slide, since we're interested in counting this, how many times the endpoint of one interval lies in the other, a basic primitive that we would like to support is to be able to use sketches to determine whether a point lies in an interval or not. This is the one-dimensional case. So we need some way to sketch an interval and a point. So one possible way to sketch an interval is by adding the psi values for every point in the interval. So the sketch of interval AB is got by adding the psi values for every point in the interval because the domain was discrete, which is not a big problem because when you represent them on a computer, you typically be using some finite precision. So now, in order to determine whether a point C lies in an interval AB or not, you just multiply the corresponding sketches. So you sketch a point C by its corresponding psi value. You multiply them. And similar to the analysis I showed before, on expectation, you will get a count of 1 if and only if the point C lies in AB. Because if C lies in AB, then C will match exactly one of the psi's here. That term will survive, the other terms won't. And otherwise, you get an expectation of 0. So we call this the simple sketch. Now, there are a couple of problems with the simple sketch, both in terms of update time and space. So the update cost depends linearly on the interval length, since you're using every point in the interval to sketch the interval. This could be unacceptably high for large intervals. Similarly, it can be shown that the variance of the estimates, if you use every point in an interval to sketch the interval, the variance of the estimators you get are very high, and this will imply very high space bounds. So in order to deal with this problem, we'll use the concept of dyadic intervals. Dyadic intervals are nothing but intervals whose lengths are powers of 2. So assume without loss of generality that your domain size is a power of 2. So in this example here, assume that your domain size is 32. So these are the points in your domain. Dyadic intervals are defined to exist from levels 0 through log n. So you define it from level, in this case, from 0 through level 5. And the dyadic intervals at level I consist of intervals whose lengths are 2 raised to I. And they partition the data space into non-overlapping intervals. So the dyadic intervals at level 3 are intervals of length 8. Dyadic intervals of length 0, level 0 are these individual points in the original domain. We'll be using D to denote the set of all dyadic intervals over all levels over n. So we define the dyadic cover of an interval AB to be the smallest set of dyadic intervals that exactly covers AB. So for example, consider this toy example where your domain size is 4. This is the set of all the dyadic intervals for a domain size of 4. So the dyadic cover of R, dr, is delta 2, delta 6 because it can be shown this is the smallest set of dyadic intervals which exactly covers R and can also be shown to be unique. Similarly, define the dyadic cover of point A to be the set of all those dyadic intervals which contain that point. So the dyadic cover of the upper endpoint of R, d of ur, is delta 6, delta 3, delta 1 because this is exactly the set of dyadic intervals which contain that point. And it's not hard to see that the dyadic cover of an interval and the dyadic cover of an endpoint will contain at most order log n elements. And this is what we'll be exploiting to reduce our complexity from the update time, which was linear on the interval length. So we'll be defining dyadic sketches for intervals and points. So the dyadic sketch of an interval AB is denoted, we'll be denoting it as psi star AB, and obtained by adding the psi values for every element in the dyadic cover of the interval. Similarly, the dyadic sketch of a point C is denoted by psi star C and is obtained by adding the psi values for every point in the dyadic, for every element in the dyadic cover of C. And the key observation here is that a point C lies in an interval AB if and only if the dyadic covers of the point and the interval contain exactly one common element. So going back to this example, the upper end point of R lies in S because the dyadic cover of the upper end point of R and the dyadic cover of S contain exactly one common element, which is delta 3. So based on this observation, you can show that the point C lies in an interval AB if and only if when you multiply the corresponding dyadic sketches, you get a count of 1 on expectation, otherwise you get a count of 0. So now that we know how to sketch a point and an interval, how do you construct sketches for a data set? We maintain two sketches for a data set R. The interval sketch xi and the endpoint sketch xc, I denoting interval and e denoting endpoint. So the interval sketch is obtained by adding the dyadic sketch interval sketches for every interval that lies in the data set, and the endpoint sketch is obtained by adding the dyadic point sketches for every endpoint that lies in the data set. So these are the two sketches that we will be maintaining for each data set. And here's how you might want to do it on the fly. So if your domain size is 4, this is the set of all the dyadic intervals over this domain. You begin by initializing your counters to 0, the interval and endpoint sketch. When an interval R appears on the screen, you first compute the dyadic cover of the interval R, which in this case happens to be delta 2, delta 6, add the corresponding psi values to your interval sketch, construct the dyadic cover of the left endpoint, add the corresponding psi values to the left endpoint sketch, the dyadic cover of the right endpoint, delta 6, 3, 1, and add the corresponding psi values to the endpoint sketch. So it's very easy to compute these sketches on the fly. And note that if an interval is deleted, you just do the converse. Instead of adding, you just subtract off the corresponding values. And the values that you get in the interval and endpoint sketches are exactly the same as what you would have obtained if the deleted values had not been inserted to begin with. So we'll be constructing these atomic sketches xi and xe, the interval and endpoint sketches for a dataset R, and similarly we'll be having an interval and endpoint sketches for a dataset S. Now we want to use these to count how many times an endpoint of one interval lies in the other, and vice versa. So you're given these two intervals. If you take the interval sketch of R and the endpoint sketch of S and you multiply them, you get a count of 1 for every endpoint of S that lies in R. And note that for simplicity, I'm showing it as though you're sketching an interval with every point in the interval, but in reality you'll be using dyadic sketches here. Similarly, if you take the endpoint sketch of R and the interval sketch of S and multiply them, you get a count of 1 for every endpoint of R that lies in S. So your estimator, as we showed that for every pair of overlapping intervals, you get a count of 2. So your estimator is going to be interval sketch times endpoint sketch plus interval sketch of S times the endpoint sketch of R divided by 2. And note that both terms are necessary. So it's not always true that both terms will contribute a count of 1. So for example, when one interval is contained in the other, one of these terms, so when you take the interval sketch of S and the endpoint sketch of R, you get a count of 2, whereas when you do the converse, you get a count of 0. And can be shown, so assuming again that there are no common endpoints, that on expectation, your estimator Z has the right value, that is the cardinality of the overlap join. So in order to determine the space requirements, we need to bound the variance of our estimator. So it can be shown that the estimator has variance bounded by half the product of the cell joins, with the cell join size is defined as the sum of the second moments of the corresponding sketches. And by using space W, which is this quantity here, which is proportional to the variance, you can estimate your size of the overlap joint within your required error bounds of epsilon and delta. So what are the space and time requirements for this overall technique? So for each atomic sketch, you basically are storing 4 counters, xi, xc, yi, and your seed, which is logarithmic in the domain size. And the time required to update each atomic sketch is logarithmic in the domain size, because the dyadic cover can contain up to order log n elements. So the overall storage cost is order W, since you'll be storing order W atomic sketches. The query cost is again order W, since to return an answer, you're basically doing some form of averaging and medians, which can be done in linear time. And finally, the update cost is order W times log n, because each atomic sketch has order log n times update cost. So note that all of this only works if you assume that the two joining data sets do not have any common endpoints. What if you do have common endpoints? So there are two possible approaches you can use to handle common endpoints. One is to modify the sketches itself to keep track of the case when you have common endpoints and subtract off the overcounts that you get for the case. And the second approach is to transform the data sets such that the transformed data sets do not have common endpoints, but the size of the overlap join is the same. In the interest of time, I just talk about one of these approaches, how do you transform the data sets to take care of common endpoints. So the way you transform the data sets is, if your original domain was n, you create a new domain m, which contains every point of the original domain. And in addition, for every pair of points I plus 1, every pair of consecutive points I plus 1 in your original domain, you have two new points, I plus and I plus 1 minus, which are ordered as shown. And what you do is you take one of the data sets, say S, and you transform it by shrinking every element that lies in the data set. So if you have an interval S in your original data set, you shrink it to form an interval S prime. So if its original endpoints were I and j, your new endpoints are I plus and j minus. You just shrink it by a small amount. And now it's easy to see that R and S overlap if and only if R and S prime, the S prime is a shrunken version of S, overlap. And secondly, so the data sets R and S prime, so capital R and capital S prime, do not have any common endpoints, and the size of the overlap joint is the same. So you got rid of the problem of common endpoints, but this has come at a cost. You increase your domain size by a factor of at most 3. But as we showed that a sketch costs scale logarithmically with domain size, this is not a very significant addition to the cost. So are there any questions? No, so I think yes. So this is how you handle the one-dimensional case. Okay, let me move on. So let's see how one can generalize to higher dimensions. So I'll talk about the two-dimensional case, and generalization to higher dimensions is analogous. So in the two-dimensional case, you're interested in the spatial joins of rectangles. So if you look at the one-dimensional axis parallel projections of these rectangles, you have the same 6 spatial relationships that you have for the one-dimensional case. And a pair of hyperrectangles is said to overlap if and only if the projections on all dimensions overlap. So for example, in these two cases, we said the hyperrectangles overlap. In this case, there is no overlap because if you look at the projection on the x-axis, there is no overlap with the corresponding intervals, and so on. So what is the counting procedure for the two-dimensional case? So in the two-dimensional case, what you'll be counting is the number of corners of R which lie inside S and vice versa, and also the number of horizontal edges of R which intersect the vertical edges of S and vice versa. And you can show that you'll always get a count of 4 for intersecting rectangles, which is basically a count of 2 for each dimension. So here's an example. Suppose you have these 6 rectangles. When you count the number of endpoints of one rectangle which lie in the other, you get these orange points. And when you count the number of horizontal edges of one rectangle which intersect the vertical edges of the other, you get these blue points here. You always get a count of 4 for intersecting rectangles, and it's basically corresponds to the 4 endpoints of the overlap region. So how do you sketch these 2D objects to keep track of these 4 endpoints? So in the case of these two rectangles R and S, these are the 4 points we're interested in keeping track of. So if you take the area, sketch the area of R somehow, and you sketch the endpoints of S and you multiply them, you get a count of 1 for this black dot shown here. Similarly, if you sketch the area of S and the endpoints of R, you get a count of 1 for this black point here. When you sketch the horizontal edges of S and the vertical edges of R, you get this black point, and similarly the 4th black point when you do the opposite. So you need some way to be able to sketch the horizontal edges of R, say, and the vertical edges of S. And the way you do it is very simple. To sketch the horizontal edges of R, what you do is you take the interval sketch along the first dimension and you multiply it with the endpoint sketch along the second dimension. So the first dimension, the extent is A through B, so you take the interval sketch along the first dimension, and the second dimension, the extent is C through D. You take the endpoint sketch along the second dimension. And we'll be denoting this as the sketch X and E, I indicating the interval sketch in the first dimension, E indicating endpoint sketch in the second dimension. And note that we'll be using independent families of psi variables for each dimension. So psi1 and psi2 are independent families. Similarly, to sketch the vertical edges of S, you take the endpoint sketch along the first dimension and the interval sketch along the second dimension, and you just multiply them. So basically, you can treat each dimension almost independently. And so note that we'll be using independent independent families for each dimension. Similarly, if you want to sketch the area of R and the endpoints of S, to sketch the area of R, you construct the sketch XII. It basically says take the interval sketch along both dimensions. To sketch the endpoints of S, you take the endpoint sketch along both dimensions and you multiply them. So these are the 4 sketches that we'll be maintaining for the two-dimensional case. And as I said, we'll be using independent families for each dimension. And the important thing you can show here is that 4-wise independence within a family suffices. So even though you move to higher dimensions, within each family of random variables, you do not need any more than 4-wise independence. And this is important because as you need more higher and higher levels of independence, you need more space to generate these psi variables. So these are the 4 sketches that we'll be keeping track of for the two-dimensional case for each data set. The area sketch, the sketch of intervals on both dimensions, the sketch of the horizontal edges, the sketch of the vertical edges, and the sketch of the endpoints. And your estimator is simply area sketch of R multiplied by the sketch of the corners of S plus the sketch of the horizontal edges multiplied by the sketch of the vertical edges, and so on. And since you'll be getting a count of 4 for every pair of overlapping rectangles, you just divide by 4. And this generalizes very simply to d dimensions. So in the d-dimensional case, you maintain atomic sketches xw for every string w over the alphabet IE of length d. And basically, to compute xw, you just look at the jth letter in the string w. If it is I, use the interval sketch in the jth dimension, and the jth letter is E, you use the endpoint sketch in the jth dimension. And your estimator is Z, is basically got by adding up over all strings W, XW, YW star, where W star is the complement string of W obtained by replacing I by E and E by I. And you scale it down by a factor of 2 raised to D because you get a count of 2 for each dimension. You can show again that you correct an expectation. Your variance is bounded by this quantity shown here. And so using space proportional to the variance, you can estimate your size of the overlap joint in epsilon delta, and note that we do suffer from the curse of dimensionality. Space requirement depends exponentially on the dimension. So these sketches can now be extended to handle other queries such as epsilon joints, range queries, and containment joints. In the interest of time, I'll not be. So containment joints are basically the case we're interested in joining rectangles only if one rectangle contains the other completely. So not overlaps, but containments. And in the interest of time, I'll not be talking about this, but if somebody wants to talk about it, we can talk about it offline. So let's move on to experimental results. Are there any questions about the sketching technique? Okay.
How would you handle? Can you handle selections over?
Yes. So basically, you need to modify I think it's better to explain offline, but it's very easy to extend this to handle selections. So basically, the question is, can you handle selections? So if you have a join of two spatial relations, and you're only interested in a selection in a particular region. So you're only interested in joining those rectangles which lie in a particular region. Whether these sketches can be extended to handle those queries, answer is yes. With the only caveat being that space requirement depends inversely on the size of the selected area, or basically inversely on the size of the result. So if the selection area is such that the size of the result is small, your space requirement is going to be very high. But this is not a problem specific to sketching, but any estimation procedure which provides guarantees. If smaller the quantity you're trying to estimate, it's going to require more space. But
it can be any kind of selection, point selection.
Yeah.
How do you work for continuous?
No, but there is, so basically when you store data on a computer, there's no concept of, So in practice, you never really have continuous real value domains. Because these techniques crucially depend on the fact that they're not continuous. So for our experiments, we basically compare the performance of the sketch-based techniques with Euler histograms and geometric histograms. These are the two best-known techniques for spatial selectivity estimation. And both approaches, so as the name suggests, are histogram-based techniques, and they operate by partitioning the data space into a grid of equibit cells. And they mainly differ in the kind of data that they store in each bucket. So they store information such as the average height, average width, or the average area of objects which lie in a given bucket. And the Euler histogram, besides allocating buckets for grid cells, it also allocates buckets for grid edges and grid vertices. None of these techniques provide any sort of guarantees of the quality of the approximation. So for experiments, we experiment with real life and synthetic data. Synthetic data, we use Zipfian data, with Zipfian skew parameter was varied between 0 and 1, 0 implying uniform data and 1 implying skewed data, highly skewed data. The skew in each dimension was generated independently. The domain size was varied from 16K to 64K, and the dataset size was varied from 30,000 to 500,000 spatial objects. For the real-life datasets, we use the same datasets used in the Euler histograms paper. These are real-life datasets containing information about the land cover, land ownership, and soils in the state of Wyoming. The size of these datasets varies from 14,000 to 34,000. So note that the sizes of these datasets are not very large. But as we shall see, the error guarantee and space requirements do not depend on the length of the datasets, but on the distribution of the data. So as long as the distribution remains the same, the space requirements and the error guarantees do not change much with the length of the datasets. So these are the results for synthetic data. So on the y-axis, so on the left is for Zipfian 0 and right for Zipfian 1. On the y-axis, you have the relative error, on the x-axis, the dataset size. So as can be seen, sketch-based technique performs better than the other two techniques, but more importantly, as the size of the data set increases, this, it can be seen that the error does not significantly increase with the length of the data set.
So what is the query here that you're?
So here I'm just calculating the overlap join of two data sets.
Sorry, what was the size of the sketch again?
Oh, the size, okay, yes, that's a good point, sorry. So basically, since none of these other techniques provide any sort of error guarantees, so what we did was we gave the same amount of space to all three techniques and plotted the error to get these graphs. And the amount of space that we gave here was 36,000 words. 36,000 integers. So these graphs show how the actual and theoretical error guarantees compare.
Why do you give that specific number?
Oh, that's basically these histogram-based techniques. They use of grid cells. The number of grid cells they use is a power of 2, and so for particular values of they operate on powers of 2, and the amount of space required is varies actually discretely. So we used a point which satisfies the required, for which you can define the histograms for both those techniques.
And the sort of this is two-dimensional data. So for the 500,000 objects, you need 500,000 times 4
for exact answers.
For exact
Yeah,
answers.
yeah.
So basically, the amount of compression you get is never more than about 50.
How much?
A factor of 50. Because you need 36,000 values.
So 36,000 by 500.
36,000 by 500 is, yeah, that's
Much less than 10%, right?
Sorry?
Much less than 10%.
Yeah.
Yeah.
No.
No, and also the important thing is if the dataset size is increased. I haven't shown it, but we've experimented with several dataset sizes, and this is not an experimentally shown fact. You can show by analysis that the space requirement depends on the distribution of the data, and not significantly on the length of the dataset. So even as the dataset now size goes to 1 million and higher, the space requirement is not going to increase.
So what gives you the worst terms of compression? What sort of distribution is the worst in terms of?
So in terms of compression, the worst case is basically when the size of the join is small. So if the two data sets are such that the size of the join is 0, in principle you need infinite space. So basically, smaller the join size, the more the space required. And but this is not a problem with only sketches. It's going to be a problem with any technique which attempts to provide guarantees.
Is it because you're going after a relative error?
You could, in that sense, for very small things, whether that is the right
That's
definition of
exactly.
that
So,
we can
yeah,
control.
yeah. You may not want to use sketches for if the join size is very small.
No, if you use absolute error, maybe you're fine, right, at that point. So even if your, join size is 0, and you say, okay, I want answers which will give me plus or minus 500, not minus, but 500 or less. Maybe. I don't know whether you can.
You're talking about relative error here, aren't
Yeah,
you?
yeah.
Whereas if you talk about absolute error, it might be better.
For smaller, yeah, it makes more sense also for smaller, as values become smaller. So there are some error metrics which take that into account. As the size becomes smaller, they call it sanity bounds. You switch to different error measure. But so basically,
sampling does have, not for spatial queries. I don't know about spatial queries. For normal point queries, sampling does have a property that fixes sample size. Above a certain result cardinality, it gives you some kind of guarantee on the relative error. But below a certain cardinality, well, the absolute error is sort of out. It's not.
yeah. So but that's basically the same problem with all techniques. Right? Same.
If you want to get ratio error,
Yeah,
relative error,
There's something fundamental.
Yeah. So these graphs show how the guaranteed error bounds varies with the actual error bound. So in this case, on the y-axis you have the errors. On the left graph on the left you have actual error. On the right you have, on the x-axis you have size of the data set. So for a guaranteed error, relative error bound, say 0.3, the actual error bound is much lower. And note again that this is not increasing significantly with length of the data set. On the right you have this space requirement. So this is a theoretically calculated value. And again you see the space requirement does not increase as long as the distribution of the data does not change. So these are the results for the real life data sets. So we basically chose to say, did all possible joins, 2 of the results are shown here. So on the y-axis again you have relative error, I'm sorry it's getting cut off out here. On the x-axis you vary the space allocated to the 3 techniques. And here what you notice is that the performance of the sketch-based techniques and geometric histogram techniques are comparable, with sketches being marginally better. But here is where you notice that interesting phenomenon with the Euler histograms in this case. that as the space allocated to the technique is increased, the error is actually increasing. And robustness, as I said in the beginning, is a very important property in practice. You do not want a system where you give it more space, your summary structure, and your system ends up performing worse.
Go back to that previous slide.
Yeah.
So I'm sorry, do you have any intuition as to why it is that you're seeing this decline?
Yeah, like I said, so increasingly.
Yeah.
So like I said, basically the estimation procedures that they use, they work only very well when either the grid size is very small, large compared to the compared to the object sizes, and the object size is more or less uniformly distributed, or the grid size is really small compared to the object size. So, and when the object size and grid size become proportional, come close to each other, these techniques tend to overestimate. So what they do is they assume that every pair of objects which lies in a given grid cell, as the grid cell size becomes smaller and smaller, every pair of objects they assume that which lie in the same grid cell also intersect a given grid cell, they also intersect each other,
So
which is true for very small data sets, but for very small grid cell size. But at a certain size, this assumption starts creating problems.
So they double count for when the objects in the grid.
Overcount rather than double.
Yeah.
Overcount.
Okay, so question with this. It looks like the Euler histograms do very well with 2 kilowords, and you don't even beat it with 35 kilowords with the sketch. So you can say that it's bad as space allocation increase, but why give it more space? Keep it small.
35? 18 kilobytes.
That's true, but it just happens to be in this data set, right? In the other.
Well, there it's close.
It's not even happening there.
Yeah.
It's close, but but this is just the property of the data set. So this is.
Yeah. So do you have these similar results for the other synthetic data?
No, for synthetic data, all is better.
No, but this is a different graph. You don't have a graph.
Oh.
Isn't your difference something to do with guarantees as well?
Pardon?
Isn't the big difference?
No, that is definitely a case why we would want to use sketches, right? That they provide guarantees in this robustness. But for this data set, for example, it is a good point that, and in this case, it happens to be the case that Euler histograms give lower. But if I remember correctly, for synthetic data sets, we have always beat Euler. So, which is not synthetic for Zipfian data sets, say. And since Euler histograms really don't give guarantees, you have no way of knowing whether they'll be beating you or not. But it's a good point actually. So in this case, you could have.
So do you have any feel for so this sample that you have here then is clearly not Zipfian, right?
Yeah.
Do you have any feel for the extent to which spatial data is Zipfian? I mean, there are cases where Zipfian is very commonly used, but is it clear that Zipfian is a good approximation for spatial?
So personally, I actually don't really have a very good feel of this, but I have. So but only just in terms of papers I've read, people seem to believe that Zipfian's Q is prevalent. I just seem to believe they're using it for some reason. I don't know.
Okay,
database
people and non-database. Database are highly suspect. They only know.
This
is non-database people's paper you are citing. I'm with you. Okay. With
I guess no. I'm citing.
They only have Zipfian distribution.
I'm citing. Yes. Mostly. There is. So one of these papers was. I guess they're all published in database conferences.
So Zipfian. So it would not clear to me what Zipfian means in this case, or what anything, because you've got a number, you've got position,
you got length,
density, and you got size, right?
So basically, all three parameters are Zipfian with different Zipfian values. So you can have each. You can vary the length in a Zipfian fashion and one of the endpoints in a Zipfian fashion for each dimension.
So Falutis used, at least for locations, Falutis used various fractal dimensions.
Yeah.
Could I make a faux pas here?
So, no, actually that's an interesting point. There was, I think, Falutsas or someone, they assume that the data has some fractal nature.
Yeah.
And so what they do is, in their techniques, they try to scan the data set and figure out what the fractal dimensionality and parameters are. So it's like parametric estimation. They estimate these parameters, and then now when you ask how to estimate the size of the joint, they use these parameters to estimate the size of overlap joins, which.
But they've also measured the fractal dimension of various real data sets as well.
Okay, and they.
Well, and I think for a two-dimensional thing, they, I think concluded was at 1.5 was the actual fractal dimension or something like that.
Okay, it's not clear. So I don't know what the findings were, but it's not clear that data would exhibit fractal behavior.
Sigma 96 could be generated using fractals.
So yeah.
Usually the selectivity estimation is to decide between different access paths.
Yeah.
So you want to say, for example, if you just have a range query, I want to use an index or I want to scan the data. So you want to use the index only, the selectivity is somewhat lower. So for on the range of selectivities where you would prefer where there is a choice, where the choice is towards index or something like can you select the extent, or for a join example, what would be the example choices you would make using the estimate for join, for a two-way join?
So exactly like
the hash join, or I don't know what are the options which are out there.
Yeah, there can be an index loop join.
Index loop join.
Hash join is
not hash join.
It's
for
not
this merge join versus
index nested loops. Or merge join also.
But even there, you want to distinguish, like you would prefer an index nested loop only if the selectivity is small.
The index nested loop versus simple nested loops. Yeah, and yeah, you would prefer it when the selectivity is actually small.
For the range of queries where the thing is actually small, how good are the errors? There's a
okay.
lot of
okay, yeah. So like I said,
guarantees are good when the results
guarantees
are
are good when the results are large, which seems to be a problem. But let's turn the problem around. So what this can do is you can identify the cases where the result size is large, right? So two things. One is you can identify the cases when the result size is large very accurately. So you avoid bad plans. So like I said,
if the result size is large, can I tell?
You can't. But that's bringing to the second part of it. So even when the result size is small, you do not get arbitrary answers. So even when the result size is small, the answer that you get will violate this error bound epsilon, but it will give you the answers with some other epsilon prime, which depends on the ratio of the actual space requirement and what the theoretical requirement was. But it's not going to give you arbitrary off answers. So if it says you need so much space and you give it slightly less space, it's not that the answers are going to be arbitrarily off. It's going to be off proportional to the difference between the two answers. So you're not going to be doing too bad. So for the cases when, for example, the joint size is large, you can easily you can assume it's large and avoid those plans at least. And typically in query optimization, your aim is to avoid the worst plans as opposed to choosing the absolute best plan. Right?
So have you had any experiments on just ordinary range?
Let's move on, and then take the sort of questions after that.
So to summarize, basically, I presented a framework for approximate query answering for spatial queries. I call it a framework for two reasons. One is it can handle multiple types of spatial queries. And secondly, you're not constrained to using these AMS sketches. You can actually use any other technique which can be used for, which produces guarantees for joint size estimation. So for example, those are recently proposed count-min sketches which could be used instead, or any other technique developed in the future. These are the first techniques which provide quality guarantees for spatial data. They can be constructed in one pass over the data and incrementally maintainable, so could potentially be used for even streaming data, or in case, say, for example, you're tracking moving objects. And as I said, these techniques are robust in that the more space you give them, the error is bound to go down as opposed to some of the other techniques. And robustness is important quality factors that you would like to have. So finally, let me just give you a quick overview. Do we have time?
Sure.
Okay, quick overview of some of my other work in the area of data stream processing. So most work on data stream processing. So most of my work is focused on approximate query answering over data streams. And so the focus in data stream processing is on developing one-pass algorithms which use limited memory to process the data. And except for very simple queries, you can usually show that finding exact answers in one pass with limited memory is infeasible. So approximations become necessary in the data stream scenario. And sometimes they are also desirable. So for applications with real-time requirements, finding approximate but timely answers is sometimes often preferable to finding exact answers return after a relatively long delay. So there are two main approaches for providing approximation to the streaming data. One is via load shedding. So if you do not have enough resources to handle this high stream rates or enough memory or enough CPU, typically what you do is you can drop some of the input tuples so that your performance degrades gracefully. And the question here is which tuples do you drop so as to minimize the impact on your answer. The second approach is via data summarization, where the idea is to build some summary structure over the stream data. And when you ask some query over the data, instead of going back to the stream data to answer the query, we use the summary structure to give estimates of the answer. So I worked in both of these areas. So in the load shedding space, there had been lots of prior work, but none of the proposed techniques in literature, they either do not handle joins at all, or if they handle joins, they assume that the inputs of to the join are uniformly distributed. Now, this is clearly not a realistic assumption. So in a Sigmund paper, we handled the problem of load shedding for streaming joins. We gave optimal algorithms for load shedding for the case when you are joining two relations, two streams, and for more than two streams, we showed we gave some hardness results, but also gave some approximation algorithms. In the data summarization space, I worked on sketch-based and sampling-based techniques for stream summarization. The sketch space, I worked on sketches for spatial data, which is what I talked about today. Sketches for distributed streams processing, more specifically on estimating the number of distinct elements in a set of distributed streams. And this has applications in areas such as detecting distributed denial of service attacks. And actually, we handle some more complex queries than just distinct counts. We handle queries such as, so if you have multiple streams that are at multiple sites, not only how many distinct elements are there, but you can ask queries like how many elements are common to streams A and B but are not present in stream C. So you can ask arbitrary set expression queries. Also work on techniques for approximating correlated sums. The idea is to analyze correlations between multiple attributes in a stream with multiple values, multiple dimensions.
So how does the result for distinct count estimation relate to other non-negative results in distinct count estimation?
So I'm not sure I know what negative results you're talking about.
Okay, we can put it offline.
Yeah. But so basically, one very nice feature about this work here is that it gives you a technique for sampling in the presence of deletes. So there is no known technique in literature which can provide you the sample when there are deletes which handle the worst case scenario. So for example, if you're interested in so typically sampling algorithms, in order to give guarantees, they need a certain known sample size, right? So suppose your stream has inserts as well as deletes. It might happen that your sample gets deleted, or your sample violates this minimum size that you need. So, and as a very pathological example, consider for each scenario you wanted a sample of size 10, say from your data, and your data set your stream had 1,000,010 inserts followed by 1,000,000 deletes. It is very likely that your sample will be empty. So the techniques developed here, the sketching techniques we developed here, with very high probability you'll be able to tell you exactly what those 10 elements are, and they use space proportional to this 10 as opposed to space proportional to 1,000,000. Yeah, it's a very interesting thing. So besides data streaming, I also worked in areas such as distributed algorithms and self-tuning databases. This work was done here at Microsoft. So in distributed algorithms, I worked on a group membership protocol called SWIM, which is basically an epidemic or gossip-style protocol, and for maintaining group membership. So you have a set of nodes, and you want to know who's up and who's down, who's working, who's crashed. And this protocol has two very attractive features. One is the time to failure detection and the load per member, on average, are both constant and are independent of the group size. So typically, most known group membership protocols did not scale well because either they have the load which increases with the size of the group, with the number of nodes you're monitoring, or if that does not happen, they compromise on the failure detection time. So in this algorithm, both the time to failure detection and the load per member, on average, are constant. So it's a very scalable protocol. And the work with self-tuning databases that I did here was based on trying to automate layout of relations on disk. So typically what happens in databases today is that if you give a database administrator a set of disks to store his relations, he'll use some form of RAID and strike his relations across all available disks. So what we argued here was that this need not necessarily be an optimal configuration, because it might happen that if you have queries which access say two relations at the same time, and those relations are stored on the same set of disks, a lot of random seeks are involved as the head shuttles between fetching tuples for the two relations. So we basically developed an algorithm which tries to automate this process of finding what is a good layout to use based on workload information in the form of a SQL workload. So you're given a SQL workload and you're given a set of disks, which hypothetical what if kind of disks where these disks do not exist. So what is the best layout to use so as to try and minimize the running time of these queries?
So did you consider at all, I mean, sort of the robustness aspect? One of the nice things about the random placement is...
No, yeah. So this is a very preliminary work. it does not take robustness into account. It's also other thing we would like is to make it incremental. So you already have a layout, you want to minimize the changes. And I think the biggest, okay. I guess that ends my talk. I'll be happy to answer any more questions that you have.
So in the experiments which you showed, how does the performance mapping compare for the three techniques? In terms of how long does it take to?
So that's actually a good question. So the sketch-based techniques, so geometric and Euler takes a little more than geometric, so they take of the order of a few seconds, while the sketch-based techniques take the order of a few seconds to minutes. Sketch-based techniques are much slower, but that's only for these AMS sketches. So if you, so like I said, there's this new sketching technique called count-min sketches. These are much faster, and they have performance times comparable to Euler and geometric histograms.
Is it? I mean, I talk about the building time. I talk about the estimation time.
Building time, but estimation time as well actually. So estimation time is not going to be observed. So building time we're talking about.
Yeah,
So these minutes and seconds of building time for data sets of size, say 500,000. Estimation time is much smaller, but basically estimation time, for example, for sketches is proportional to the size of the summary structure, while for histograms it's much. No, for histograms also it's. So estimation time is probably comparable.
So do you have any results for that by chance? Do you have this?
I don't have the numbers here, but I might have the numbers for. So I might be able to show you the numbers for the faster sketches or the slower. I can have it offline, so I'll show it to you.
The other question is that suppose for sketches you assume a log n size, right? You have to have it. Suppose you don't have that one size, it's below log. So how does the error change there? Do you have any ways of creating some approximate results here?
I mean, basically, if you don't have order log n space, you can't even start with sketching. I mean, you need to be able to generate these psi values, right? If you can't generate them, I think all bets are off.
No, at generation time you have, suppose. Seed is not, you don't store the seed, right?
I store the seed. That's exactly what I store, because I don't want to store the psi values. So I store the seed instead. And every time you want to know a particular psi value, you use the seed to figure out what that corresponding psi value is.
No, but once you build the sketch, suppose you have the xi, xie.
Oh, then I can. Then I can use. You're saying I can drop off the.
Yeah,
sure.
need the seed.
But then, in that case, but then your space requirement. Note that it actually. So these formulae are slightly deceptive because they also depend logarithmically on the length of the streams, which I haven't shown. Basically, because these counters, I've assumed they're constant space. You typically assume the constant space, but so clearly since they're counters, they require space proportional to the log of the stream size. So you need to have actually space proportional to the log of stream size plus the log of the domain size. Now, if you have, for example, at build time, suppose you have space proportional to log n size, then you're fine. But you need at least log m size, the domain size. But you need at least space proportional to log of the log of the size of the streams.
But that has to be there because you have to store at least one frequency. I mean, that's what you're saying.
Yeah, I mean, if you have less than space, I think all bets will be off.
Just one number.
One reason I was asking was that your histograms can work below that space, right?
No, yeah, so like Venki said, he had a good point, right? That basically it's log n, and log n basically is if just using one number, you're already using up the space. So if you even store one object, and histograms typically are not even doing any compression. So when you're sketching, you're using these hashes and you're at least transforming the space. In case of histogram, you're typically just storing the exact endpoints. So you will be using order log n space anyway. So you'll be using order log n space, right? Because in histograms, you typically store the endpoints. So
what are the histograms in the scale up with dimensions?
I mean, all of the techniques obviously perform very bad as the dimensionality increases. All of them have this curse of dimensionality. You're asking in terms of
space requirement.
So histogram, of course, you can't say. I mean, there's no formula. I can talk about the sketches. Sketches scale up as like of the order of with 1.5 raised to d. The d is your dimensionality. So I mean, that's all I can say for now. So, the histograms don't have any guarantee, so you can't really say how this scale up unless you want some experimental numbers, which I don't have top of my head.
Why is it 1.5? It's kind of weird.
It just happened that the variance.
Oh, it's 3 over 4.
3 by 4, and then there's a factor of 2 raised to b sketches. So I mean, it just happened to be the case. That's how the math worked out. Any other questions?
So you're saying computation time for sketches is feasible. So building the sketches is feasible. I mean, how much time does it take for 500,000 or I mean, let's say 1,000,000 objects?
A million objects, right?
Million
It
sketch
take of the order of like a minute, 2 minutes.
Where does most of that time go? Is that just getting the random variables from the C?
Yes. So the problem where you spend most of the time is that for each update you need to update your entire summary structure. For each input interval you need to update all these atomic sketches, every atomic sketch. So you're touching your entire summary structure for each input. For histograms you just touch the corresponding cells, so you're much faster. But these new sketching techniques, they touch only a constant amount of space. Log 1 by delta, where delta is the probability guarantee you're interested in. So they are much faster, but they provide some sort of different guarantees. So
Got it. Okay.
Yeah.
So I understand for spatial data, the random sample cannot give you any error guarantees, right?
No, I'm not saying cannot. It's possible, but yeah, it's conceivable that it could.
But I mean, you can still use it for comparisons. Like, did you do any
Yeah,
comparisons?
so I didn't do it. Somebody else did it before me in 2001, and they found histogram techniques to perform much better experimentally.
Which they have.
The histogram technique, the
Euler and geometric histogram. I think that was the paper which proposed geometric histograms. So they compared sampling-based techniques and they found geometric histograms to be superior.
Okay, but you didn't do it.
No, so and I mean the conclusion was it's better to use histogram-based techniques. So we just used.
It's probably true for lower dimensions. That's what.
They use normal plain hash functions instead of those polynomial multiplications, blah blah blah, for your sketch building.
Yeah. So instead of actually strictly speaking for the sketches you're supposed to do operations in the finite field, and so which also will add to the time required to build a sketch. We used a hack there, and so I was telling Raghav about it. So basically the sketch generation requires you to do operations in a finite field. So you need to compute things like j cubed in GF2, Galois field 2, x cubed for where x is some element in the Galois field, k vector.
But what is the difference in accuracy? I mean, is there any noticeable?
No, so I have been using this non-proven. I have not been using the finite field operations. I've actually been doing ordinary. When you're asked to do x cube in a field, I've just been doing x cube over an ALU or normal or arithmetic unit, and so it's possible that the guarantees may not hold, but I've never faced a problem. So. And that speeded up computation. So.
That's the reason why I was surprised that when you said million sketch computations.
No, I'm not doing it. I'm not doing it. I was telling him. So I used a hack there, and it seems to work. So it's. Yeah.
So the more efficient version doesn't need to go back and update all the sketches?
No, it updates only a constant fraction of the constant number of sketches. Of the order of log 1 by delta, as I said. So if delta was the probability guarantee you're interested in, it needs only log 1 by delta, which is just like less than 10 usually for delta say 0.9.
But then the error guarantees that you gave here,
the error guarantees will change.
There will be still some guarantees.
Yeah, definitely. But it will change according to the analysis for those structures. And so I did experiments with those techniques as well. For these datasets, the space requirement was much larger than these AMS sketches. But there are two important things to note. One is, in worst case, that will do better. And also the space requirement depends, for this technique depends on 1 by epsilon squared, where epsilon was your relative error. For that technique depends on 1 by epsilon. So as you make epsilon smaller and smaller, that technique will start being better. So there are these trade-offs involved, they're not really directly comparable. If your running time is crucial to you, you need to use those techniques. And then for particular types of data, this
only building time, so by running time you need
yeah, building time. And even estimation time, same thing. So even there for estimation also they touch only a constant number of guys, while this guy touches the entire summary structure.